So this one more simple problem using the formula for gravitational field. So the Earth can be assumed to be uniform sphere of radius r. What's the mean density of the Earth? Now we know that the formula for density equals mass divided by volume, and you have to find out the mass and the volume with the information given to us. Now the only thing we know is the radius r. Using this standard equation, the gravitational field is equal to gm by r square, where r is the radius of the Earth. So you can get the equation for m. If you reorganize this, you get m equals small g r square by the big J. Now we got the formula or the value of m. Now this is the standard mathematics formula for finding the volume of a sphere. Now the volume equals 4 by 3 pi r cube, where r is the radius of the Earth. So now you know the value of m and the value of v. You just have to divide and find the value of this. So when you substitute the value of m and v into this equation, you get, after simplification, you'll end up getting 3g by 4 pi rg, which is the answer A. So one more problem using the density. This is from June 2015 paper. So what you have here is the following table refers to two planets P and Q. So this is the information about planet P, and this is for planet Q. So planet P has a radius of 8,000 and kilometer as a density of 6,000. Planet Q has a radius of 16,000 and a density of 3,000. The gravitational field strength at the surface of P is 13.4. What is the gravitational field strength of surface of Q? Most often, if you come across two planets or two masses like this, solution will be to find the ratios of the two using information from two planets. So you have got the information about the planet P. So they are given the mass, the radius, and the gravitational field at the surface here. This is 13.4, and you got one more, the bigger mass, that is the planet Q, which has got the radius is 16,000 and the density is half. So there are a number of ways to do this type of problems. Now you have to look at the number of the marks awarded to this question. So most often if it's a 1 mark question, the solution will be pretty easy. So here I'm explaining you how you can solve these two problems. So I'm going to assume, so see, we have to find the value for planet Q. So I'm going to assume, let r be the radius of planet P, and this is 16,000, so this will be 2r. If I take this as a rho, this is the density of the planet P, 3,000 is rho by 2, and we know the standard equation. The gravitational field is gm by r square, and we know the density equals mass by volume, and if you cross multiply, you get the mass equals density times volume. So you have to just take the ratios of the gravitational field of P divided by the gravitational field of Q. So here the gravitational field of P is 13.4, they are given here, which is equal to, applying this standard formula, so g m by r square. We don't know the exact value of m. However, you can get this formula by taking the radius and the density. Now to get the m, you multiply the density by the volume, you get this value by r square. For the planet Q, let the field strength be EQ. Again, gm by r square, this one, gm. So this whole thing is the mass for the planet Q, which is the density times volume. Now again, the density is rho by 2 because we are comparing. So these type of things they will end up getting cancelled. So 4 by 3 pi, the radius is 2r. So 2r cube divided by the radius square, 2r square. Now when you take the ratios of p and q, so you will end up getting everything from here divided by everything from this formula. When you start cancelling out, you'll end up getting a ratio like this, which will be equal to 1. So when you get 1, what it means is p by q is equal to 1, or p equals 1 times q. So the answer is the gravitational field on planet Q is same as the gravitational field of planet P. So it is this one. So this is something I got. Probably this is going to help you as well. So this is the graph of the gravitational field strength, how it varies along with the distance. So I got a mass m. Now this is, you know that this graph has the shape similar to 1 by x square. So this is the point where the gravitational field is almost 0. So we are calling this as infinity. This one is a smaller mass. So when you compare with the bigger mass, the gravitational field strength of this will be reaching 0 much earlier than the bigger mass. This is still smaller mass. Now when you plot gravitational field graph for this, it will reach 0 somewhere much before than the above 2. And if you put two objects side by side and have a single graph, now this is the graph, a bigger mass, smaller mass, this will reach 0 at a much further distance compared to the smaller mass. In all my previous videos, I have been solving problems related to gravitational field by just using the value of the field. But a gravitational field is a vector quantity. It has got both the magnitude and the direction. So you should be able to draw the direction of the gravitational field as well as the force acting on the object in this gravitational field. So what I got here is I've got a spherical mass with the gravitational field lines. So these are called like a radial lines, and here I got the surface of the earth, the gravitational field lines that are perpendicular to the surface of the earth. I've got the test mass here, m and small m. So most often the test mass will be very small compared to the mass you are studying. It is usually 1 kg and 1 kg. Okay. Now let's see what's going to happen if you place a mass. Think this is the earth. If you place a mass above the earth's surface, obviously this mass is going to fall down towards the earth. Now this is also same as saying there is a force on this mass acting downwards, and this force is pulling downwards. Here as well. So I got a mass here above the earth. If you let this mass go, it will fall towards the earth, which is same as saying there is a force acting on this mass in this direction. So from this information you can find out the direction of the gravitational field. So the direction of the field is same as the direction of the force acting on the mass. So here we know that force acting on the mass is downwards, so direction of the field is downwards. Here also the direction of the field is downwards. So I'll just explain same thing here. So I got a mass m. Now this is the force acting downwards. Because of this you can say the gravitational field direction is also downwards. So here I got a gravitational field lines and I got a mass, and the force on this mass is in this direction. Now what is the field direction? So we know that the direction of the field is same as the direction of the force acting on the mass. So here also if I keep a mass, a small mass here, the force acting on this mass will be the same as the direction of the field. So the force will be acting downwards, and this we have come across before as well. This is the shape of the gravitational field strength. It is more towards the surface, means it is more towards the surface, and the gravitational field will reduce when you go further away from the surface. So sometimes you will come across a question that says, what does the field lines represent? Now the field lines represent the strength of the field. So you can find out the strength of the field by looking at the density of the lines. You know that the density of the lines near the surface is more than the density of the lines if you go away. So the closer the lines, the stronger the field. The more space between the lines, the weaker the field. It also, the field lines will also tell you the direction of the force acting on the mass. So you can say that there are two things the gravitational field lines will represent. One is the strength of the gravitational field, the other one is the direction of the force acting on the mass. Now because gravitational field is a vector quantity, you have to know some simple vector arithmetic. So there are many questions that needs the background knowledge on the vector arithmetic. So I have got two vectors here, E1 and E2. So think that E1 is the electric, sorry, I don't know, I'm saying electric, the gravitational field on this side, and E2 is the gravitational field on this side. Now we know gravitational field is a vector quantity, so the net field will be the bigger vector minus the smaller vector. Here also I got two vectors here, E1, E2. These are the gravitational fields. The net is, because the vector is in the same direction, it's the sum of the vectors is E1, E2. E1 plus E2 is the net vector. Here again it's the same as that. So what I've shown here is two vectors are same in magnitude but opposite in direction. E1 and E1 in this direction, E1 in this direction. You know that when two vectors have the same magnitude but opposite direction, the net vector is 0. E1 minus E1 is 0. So sometimes you will end up finding the resultant vector, and again you have to be little bit good in the vector operations. So here I got two vectors with the same magnitude, E1 and E1, and these are at an angle of theta. Obviously the net vector will be somewhere starting from here in the middle. This is the net, and you can apply the parallelogram to find the magnitude of the net vector and the direction. And we know that the magnitude is E1 square plus E2 square plus 2E cos theta. So by applying this calculation, you can find the magnitude of the resultant vector. So likewise I got two vectors with the same magnitude which are perpendicular to each other. The net is exactly because these are equal vectors, the net will be at an equal angle, which is 45 degree. So you have to find out the resultant vector is E square. The formula is A square. You know that the formula is A square plus B square plus 2AB cos theta. That's the formula of resultant vector. So when you apply that, you will get E root 2. So you have to know a little bit of vector addition and to find the resultant vector in order to solve the gravitational field problems. You have to know something about the uniform gravitational field. So uniform means constant or the same. Now if you look at this diagram, these lines are separated by the equal distance. So we can say that the gravitational field strength at all these areas are the same. Similarly, here I got the gravitational field lines that are converging here. There could be a mass here. So if you look at the closeness of the line, so these lines at this distance, the lines are very close. You can say that the field is strong here. At this point on the line, you can see that the lines have got more spacing. You can say this is not strong. At this point, they are still further spread out. You can say the field is weak. So by looking at the gravitational field, you can find out where the gravitational field is strong and where it's weak, and you have to remember this uniform field where the field lines are equally spaced. So this is a question from June 2015. It says the diagram shows an isolated binary star system. The two stars have equal masses m and the distance between their center is r. The point P is a midway between the two stars. What is the gravitational field strength at P? Now to do this problem, you have to know that gravitational field is a vector quantity. So this is the point, and this point is at a distance of r by 2 from this star and a distance of r by 2 at this star. Just apply the basic the formula G is equal to Gm by r square. Now at this point, the gravitational field due to the star 1 is in the direction toward this mass, and at the same point, even see both the stars have the gravitational field at the same point P. Now the gravitational field acting at distance P due to the star 2 is in this direction. So we have got, because the mass is the same, the distance is the same, the gravitational field strength will be the same. Now what I have written here is P is equidistant from 1 and 2. So P is r by 2 because r is what is given in the problem. It's the distance between the two centers. So the gravitational field E1 because of star 1 is Gm by r by 2 whole square, and E2 will be Gm by r2 whole square. If you look at this, these two values are the same. So this is like having a vector with the same magnitude but opposite direction. So obviously the net gravitational field at this point will be 0, which is this answer A. So this is one more simple problem from 2017 June paper 2. So it says Charon is a moon of Pluto that has a mass equal to 1/9 that of Pluto. The distance between the center of the Pluto and the center of the Charon is d. X is a point at which the resultant gravitational field due to Pluto and Charon is 0. This is exactly what we saw in the previous problem. Now there is a point here at the point X. So what it's saying is, at this point, it's clearly mentioned the net gravitational field is 0. It means the gravitational field because of the planet Pluto, which is in this direction, must be same as the gravitational field acting at the point X due to this this moon of Pluto in this direction. So it's clearly mentioned that E1 must be equal to E2. Now again apply the basic formula, with the gravitational field is Gm by r square. Apply Gm by, what I've done here is, so problems like this, you have to solve in, just have to make assumption here. Now I'm going to say that the distance of this point X from this planet Pluto is X, and this distance will be obviously d minus X. Look at that, the problem is already given the distance between two planets is d. If this is d, and if I assume that the distance from this planet is X, it's obvious that this distance will be d minus X. We can apply some simple concepts here. So you know that Pluto is a bigger planet and this planet is a ninth of the size of this. It's very obvious that the 0 will be somewhere near to the small planet. 0 can never happen, it can never be to the bigger planet. So just substitute into the formula. E1 is gm by x square, gm by d minus x whole square times 9. See, the mass of this moon is m by 9. If you think m is the mass of the Pluto, the planet, and the problem says the mass of the moon is m by 9. So this is how you got a 9 here. Now everything will cancel away. This will cancel away. This will cancel away. You'll be left with 1 by x square is equal to 1 by d minus x square into 9. And looks like this is a very quadratic equation. I don't think for a 1 marks you'll be given a problem where you have to solve using the calculator. Now if you again rearrange this, probably take the inverse on both the side, you'll get x square is equal to d minus x whole square into 9. Take the square root on both left and right side, you get x is equals 3 d minus x, and if you simplify, you'll end up getting x is equal to 3 by 4d, which is the answer